Thank you, Nikki, so much for that amazing workshop on fundraising and grant writing. I learned a lot, and I think a lot of people hopefully learned a lot. So now we're going to turn it over to Andrew from Team 5414 for a workshop on PCB design with Altium. I'm super excited for this one because PCB design is not something that's too common in FRC, and I think that a lot of this information can be used to can be harnessed for a lot of really cool things. And I'm looking forward to learning a lot and hopefully using some of this in the near future. So we'll turn it over to Andrew for the next hour. And yeah, Andrew, feel free to share your slides
All
and
right.
begin your presentation.
Sounds good. My name, as they said, is Andrew. I'm with Paradox 5414. I think I'll just share this whole screen. Hopefully that'll work out okay. I've been doing board design for, I don't know, roughly about 10 years now for my day job. I'm a computer engineer, graduated Purdue, and I work at NASA Johnson Space Center now. So I do a lot of programming, but I also do a lot of schematic and board layout. Typically nothing too complicated. We usually give those to the real electrical engineers as opposed to the people that do the software and some electrical engineering. But I think it was really exciting when I first noticed that Altium had a license that teams can use, since that's the software that I use at work. Yeah, it's good stuff. It is definitely complicated, and there's other stuff out there. So I wanted to get into first, what is Altium? And Altium is what allows you to design and create files needed to fabricate printed circuit boards. It's one of several different software suites available. Altium, or something like it, is what is used to create the internal electronics for a motor controller or power distribution panel, the RoboRio, all that kind of stuff. There's lots of other popular choices out there. In particular, KiCad is free open source software. And I've heard plenty of people say great things about it. That has the advantage that if you want to use it when you're not in school any longer, and you don't have a student license for Altium, it's the same software you've been using before plenty of times. There's EagleCAD, which a lot of different universities use, I think, because they have it via Autodesk. Upverter is a new thing that seems kind of like it's the Onshape of schematic design. It's through Altium, and it seems like something that you can do through a web page and have multiple people kind of working on. You get one Altium license in the virtual kit of parts. The scope of this presentation is really only about the Altium software, not so much about the design of circuits. Even as this is, I did a run through with my team this past weekend, and man, it's a lot of stuff I was trying to shove into 1 hour. So I've kind of reformatted it a little bit, and hopefully it'll go okay. We'll see how it is. Wanted to give some quick definitions of things if I've already said some things that don't mean anything to you. Schematic Capture, you can see in the top right over here. That's the layout of how things are logically connected to one another. Doesn't necessarily mean anything in a physical sense. It just lets you know what pins are connected to what other pins, and how everything logically is connected. Then there's the PCB layout, which defines how the copper physically gets routed on the board, and gives you more of an idea physically of what it will look like. I'll also use the term footprint a lot, which you'll see in data sheets. Sometimes it's called land pattern, or I don't know. I've seen a couple of different weird names for it, but it's the arrangement of the pads or the holes for the component. And so that's always very important to make sure you get right. I can't tell you how many boards I've done that the first revision has one footprint problem somewhere or another. And then at least in Altium, I'm not sure what it's called in the like KiCad or Eagle. We have schematic libraries and PCB libraries, and those are just basically where you build up and define your own schematic symbols or your own PCB footprints, which at least I tend to make my own footprints for things or reuse things that I've already done. Sometimes you can use some of the integrated things or download footprints from online, but I usually like to make sure that it meets whatever it is that I'm going to be doing it for. So like Cycron was talking about a little bit, why would you use Altium? Why would you do a custom PCB? I'll be upfront. I think the main reason to do it is if you have a student that's really into electrical engineering and wants to get that experience of board design, maybe they want to continue to do it post high school, maybe they have some hobby type things that they want to build up, or maybe they want to do it as a career. For the most part, I think there's not too many teams that will become more competitive by doing custom PCBs, but there are a couple of things that come to mind. Most of the time, it seems like vendors, once they identify a need for a new custom PCB, it'll happen. So for instance, the Aussie boards, the 775 inline power pole connector, I'll pull up this just as an example of a PCB that, you know, a few years ago didn't exist. And it's basically a real simple board. And all it is to be able to put Anderson connectors on the 775 Pros. Lots of teams love it and use it a little bit better than the terminals that you'd have to use before and hope that they kind of stayed there. But nowadays, obviously, a vendor is taking care of it. There are some times where maybe you can make some wiring cleaner or easier to maintain. This is an example of something that I don't think gives us any kind of competitive edge necessarily, but it was a way that we could try to do something. So we made a custom PCB that had these spring cage clamps. And so our motor controllers could be plugged directly into here. We didn't need to use the Wago levers. We didn't need to solder it or do any other kind of connections between the motor controllers. That works for us because we tend to put our motor controllers physically near the PDP. For other teams that you move your motor controller nearer the mechanism, maybe that wouldn't work as well. And we've been kind of tweaking this and messing with it a little bit. I think we could make this one bus and then just have a 12-inch stub or less come out to the motor controller and still be under spec and be fine with that. There's plenty of CD conversations about all of that. Then maybe you have a new great idea of something that other FRC teams should have. So I think at least the Glowworm has a custom PCB in somewhere. I think the Limelight has a custom PCB. I'm not totally sure on that. But yeah, there's some instances where maybe you do have some new great idea to do something. So I wanted to have a sample project that we did today. Originally I was going to go through this CAN board here and I just forgot to figure out, but pretty much earlier today, I decided I was going to do a totally different sample project and spent the day kind of redoing how I did that. So let's say that we want to use multiple of the Rev I2C color sensors. For instance, this year with a color wheel, maybe it would be, or you would be able to be a little bit quicker if you use 3 of those color sensors. And the Rev color sensor has one fixed I2C address. And so the RoboRio only has 2 I2C buses, one on the MXP and then one that's got its own header there. And maybe you wanted to use 3 of the color sensors. So you could look at something at the middle, left, right. So depending on which way you're spinning and know if you're in the dead center of it, I don't know. Maybe that's really important to your design or something like that. And so we could say, okay, we want to do a custom PCB that could plug directly into the RoboRio, give us additional I2C buses via an I2C switch. And then we want to make sure that we can have at least 4 devices on it just because we can. I don't know. You could do just 2 or 3 or whatever, obviously. I'll be making a step-by-step guide for this. I did make a step-by-step guide for the CAN bus. So if somebody comes back and says they want to learn a little bit about Altium, I pretty much tried to do, I've got like a 20-page document that I tried to document every little thing about how I went about making the CAN PCB here. I just want to point out, though, just to emphasize this is really more for the experience than anything else. If you look up I should have already had this up, but TCA, or let's see, yeah, TCA. So Adafruit already has this 1-to-8 I2C multiplexer. It's $7. It's already pretty tiny. You could solder a bunch of wires to this and be perfectly set. So again, I just want to emphasize, look first. There's probably a board that you could go off and buy. So if you've got limited resources or you're in a time crunch, like this is absolutely the way you should do it from a strictly, I don't know, what's advantageous to your team. But again, if you're wanting to get some experience, or maybe you've got a different situation where this thing doesn't already exist, that's where this comes back into play. So also, I always think it's unfortunate when somebody kind of jumps right into a thing. So I wanted to make sure I talk real quick. There's a link for you to go get a license for Altium. Sometimes it'll take a couple days to get it. You'll eventually get an email with a link to be able to download it and information for the license. When I went through this process recently, it wasn't as straightforward as I would have liked. But if you have some patience and kind of exhibit your best guesses at things, I think it'll work out just fine. You'll follow the instructions to set up your license. And then if you've got multiple people working on it, you can, I think, use Altium 365 Viewer to be able to download it and look at other people's changes to the schematics or whatever. You just won't be able to edit the files yourselves with this viewer. So I would probably recommend either putting it on one team computer that multiple people have access to. You might be able to get it set up where multiple people install Altium and then only one person can use the license at a time. And there's some pretty decent tutorials out there for Altium, and KiCad in particular, I'm sure also has a bunch of great tutorials since it's free open source software. So during the install process, the only thing you really need is the PCB design. Altium is used in industry a lot, and so there are some very extensive add-ons or things that you can add on to it that just take up a bunch of space and you don't need to install. There might be some things that you want to add, importers, exports for DXF or DWG or some other things. So before I go into some of the first steps there, I wanted to kind of introduce this as the Altium software here. And there's a bunch of things that are going on in here that can make it very intimidating and overwhelming the first time you open it up. This is more or less what it'll look like the first time you open up. You'll have the home page. Over here is where you would set up your licenses. So you'd sign in, you'd set up your license, your activation code that you get in an email. You see that I've got one that's expired from when I was doing this with the Gatorzillas back a long time ago. This is a newer one that we've been doing for Paradox. And yeah, so that's kind of the introduction, or what you see when you first load up. There's a big U around Altium that basically has a bunch of things that you kind of want to be mindful, unfortunately, of all sides of. The left side oftentimes is where, at least by default, the projects show up, and there's a navigator over here, and new panels will open up over here as you do things. And so this will change depending on what it is that you're doing, and sometimes you'll have to physically go change it. Same thing on the right. Typically, there's some things that get docked to the side that you can load up. So for instance, right now I've got messages and manufacturer part search as two things that are docked to the side that I can load up. But the big thing is there's this panels button down here in the bottom right. And this is where you would go if, say, for instance, I can close this projects panel. And now there have been times when I was first starting out that I'm like, oh my gosh, I don't know how to get back to my different schematics. So you would come down to your panels page and you would add your projects back in, and it will open back up. You can pin it, you can move it, you can have a floating dock, whatever. And then the last thing to watch out for is down along the left bottom here, you'll see typically either some helpful hints or some XY locations for a grid. So also be mindful of what's going on down here. So that's kind of a quick introduction to the Altium interface. I'm going to be doing more introductions as we open up different context for the different PCB Dock or Schematic Library, etc. So now that we've identified what it is that we're going to make a PCB for, a really important first step is to make sure that those parts exist. And this can take a couple of days to go off and do some research and find the thing that you like. Again, since I just started doing the I2C version of this today, there's probably some better parts out here than what I've listed in here. These slides will be available, so it can kind of be a jumping off point if anybody wants. So for instance, there's the I2C switch. This is an 1 to 8 mux for the I2C switch. And then I wanted to make sure that I got a 4-pin receptacle for the Robo Rio that gets plugged into the Robo Rio. I think that there would be a better one than the one that I've got here. And then because of the Rev color sensor, they've got extension cables that are the JST type connecting. And so I wanted to find some JST connections that we could plug in with this. The thing that you'd have to be most mindful of here is making sure that you get a connector that is the right type of locking feature. So I didn't spend a whole lot of time, but this looks similar to some of their joiner boards. I think this is an acceptable one. If I were doing this with a team, I might buy one of them. They're 73 cents. I'd be paying more in shipping than anything else. I might see if I can get some additional Anderson connectors or something and tack this on there and make sure that that fits the way that I like it. Or probably just email Rev and check and make sure, hey, would this part work? So now that we've identified those parts, you might want to take a look at the data sheets, some of those, and make sure that they're the things that you want. If I've got time at the end, I'd love to talk more about part selection because that's a really important part. So now that we've decided on the parts, we would do schematic capture. I'm going to show real quick how you would start a new project here. So you've got File, New Project. Sorry. And I'm just going to do a empty PCB project with the default stuff here. And let's just say this I2C scratch, just because this is going to be from scratch. I'm going to jump ahead through some other projects in a bit. Also, sorry if the puppy squeaking toy is audible in the background. Hopefully it's fine. And so now I've got this empty project. I've done this enough that I know what kind of things I want to add into here. So you would right click. Oh, you know what? I was going to add in Hartnett. So this is an application that will hopefully display the keys that I hit. Yeah, there we go. I do a lot of keyboard shortcuts and want to make sure people could see that. So you right click on the project. I'm going to add schematic and PCB. I don't need to now, but I would normally add like an active bomb. I'll add a schematic library. And you can see now when I opened up or added a schematic library, it changed the context on me here. It's got the schematic library panel here now. So I need to go back to projects and then do the same thing for the PCB library, which will happen again. And I'll also add an output job file. So those are some common things that I would typically do. And then I'd go ahead and save the project. So when I save the project, it's going to ask me to save all the other stuff. I'm going to be kind of lazy and just name all of them the same thing and just let the file extension do it. So if you do this and save the project and everything's the default thing, it will, whoops, I didn't save the new name there. So this can be a way to rename all your files here. In a bigger project, you'd have multiple schematic documents and you might want to name them more uniquely and usefully. All right, so we've got our project here. We'd want to go into our schematic. This is where you'd start out with. And you can't really tell necessarily, but this is a huge schematic page. I'm going to go ahead and go into I hit the properties here and I can change the sheet size. So I'll change that down to B size. I can probably go down even smaller actually, but that's fine for now. This is your blank canvas that you're going with. There's a bunch of shortcuts, P for place and P for part. And now there's all these libraries over here. So these are the two libraries that I've created. There's not going to be anything that exists in them yet. But the miscellaneous devices and miscellaneous connectors are integrated libraries that were installed with Altium. So there's a bunch of things already here. Some of them already have footprints that'll work. I'm going to lay down a couple of parts and then show you a future thing here. So I've laid down a connector here. And then a nice thing that can be useful in Altium is if you hit Shift and drag, you'll create duplicates of it. And I think actually even, so if I'm gonna show something else later, but if I name this P1, and then I shift click, oh, okay, it didn't do it that time. There's various ways that it will automatically change things. So I've got the 4-pin connector to the RoboRio, and then I've got 4 4-pin connectors for the JSTs. If we look at the TCA, that I2C switch, and look at it, we can see that it is a 12-pin small outline package. And so if we go back in here, we could also do P for place, P for part, and we could find a 2x12. So let's do that real quick. And this is just to show an example. This is not how I would do it for real. Whoops. I actually want this guy here. All right, so I could place him in here. And so you'd place things down. You'd could wire up your connections here. Some of the nice things are that you can go and edit your pin names. So you pull up your data sheet for this guy. And I thought I already had it loaded, sorry. You'd pull up your data sheet, you'd look at what your pinout is, and you would modify the pinout of the schematic sheet to match that. But something important that I want to show that I really recommend is that you actually use a manufacturer part number and assign parameters to things. So let me show you how to do that and why. So if we go back to DigiKey, I'm going to just copy this part number here. And if I do a manufacturer part search and search for it, eventually here, this will show up. There's 4 different suppliers that I could get it from. DigiKey and Mouser. Mouser has a place in Texas, so I would typically order from there. But I'm just going to right click, add supplier link and parameters to parts, and then click the part that I want to add it to. Probably beforehand, I should have deleted some of the old parts. If you double click on it or you click the properties over here, you'll see that down here in the parameters, you select all. Now it's added a bunch of parameters from DigiKey about that part. That can be really useful. In particular, the thing that I really like about it is that now when I right click and go references, it's got a data sheet link. So straight from the Altium schematic, you can right click and open up a link to the data sheet. That is immensely useful in a number of different instances. So you'd want to go and do that for all of the different parts here. You might need to add some resistors or capacitors and different things like that. And that's a little bit outside of the scope of this. So what I'm going to do is I'm going to switch to this project. Let me close others. All right. So this is something that I had in progress. I haven't actually done anything with this other than do the schematic up for it. This is where I would like to eventually get the schematic to. Obviously, I couldn't do all that in the time we've got allotted here. So something that's kind of interesting you'll notice is that I've switched, I ended up making a custom symbol in the schematic library to move pins the way that I like to, because it doesn't have to be a physical representation. It doesn't matter if SDA, SCL, and VCC are right next to each other on the physical part. On the schematic, I can put them right next to each other to keep the wiring clean and make it a little bit easier to read. So you place down all your capacitors and resistors. I've got a decoupling and bypass capacitor here. And then you match your Robo-Rio I2C connection here. Something to be mindful of is that I noticed that on the Robo-Rio, it's the data clock and then the clock. I'm sorry, the data line, then the clock. But for the JSTs, it's the clock and then the data. So that was something that I kind of caught today while doing that I wouldn't have been paying attention to otherwise. So you can see that this is a U?B and a U?A. So the A and B show that it's all part of one component, but there's multiple parts to it. And then I've also created some mounting holes. So let me show you where that happens. So here's my schematic library. And so I've defined these things in here. You'd go and add a footprint to it. And these are all the symbols that I use for it. You can see that I should rename this to be the name that I like to use the manufacturer part number. But you can see I've got part A, which is the one part, and then part B, which is the part that just goes to the Robo-Rio essentially. So then there's the PCB library, which is then the footprint of all the different components. So I've got a footprint for the JST module, one for the mounting holes, one for the 4-pin header on the Rio side, and then this is the small outline package for the I2C switch. Something that's kind of nice is that in Altium you can hit 3 to go to 3D mode. I've actually placed 3D step models of the parts on them. I find that to be helpful to make sure that I got the footprint correct, and I can go and add additional like lines if I want to about all this. I'm going to probably do a little bit of an example of that later if I can. But I find that useful to make sure that I know how big things are on the board and that I didn't accidentally use the wrong units or anything like that. So when you look at these things, you can make sure that all your pins line up and that there's no problems there. So if we go back to the project now, I'm going to show you, this is not quite finished for the schematic. One of the things that you'll want to do is learn about annotating your schematics. You can use this annotate schematics quietly for the most part. Sometimes you'll have to go into here and like reset annotations or designations, then update change lists, and then you would just hit accept changes and execute changes. There's more details as to what's going on there, but if you do that, you'll now see that we've got P2, U1B, U1A. The mounting holes are now 1, 2, 3, 4, and all that other types of stuff. So now we've got fully annotated schematics. It's also good to right click on your project and validate. And sometimes your messages window won't pop up, but in this case, the compile was successful, no errors were found. And so if we look at the PCB dock, you'll see currently it's all empty. And that's because we haven't pushed the changes from the schematic into the PCB yet. And so we've got, this is the Rio side thing. It's got a footprint tied to it. If you were doing this from scratch, you sometimes would want to go and verify your footprint model and make sure that it's what you're expecting it. And if you do the same for the JST one, oops, sorry. You can see that that's the JST footprint. When you use the integrated library, sometimes you'll have to go and manually control some of that stuff and make sure that it doesn't use the wrong one. I use the integrated footprints for the capacitors and resistors that I've added because I didn't want to do more. When you do the design, or you click design up here and click update, and what's going to happen is it's going to create this engineering change order. And you can, depending on what you want to do, you can validate changes, make sure that everything looks good before you go off and execute everything. And that will just tell you that everything happened right. So all these footprints have been placed now. And they're in something called a room in Altium. I'm assuming other things have something similar. For smaller designs like this, you don't really need them. You could actually use rooms to be helpful in this case, because if we look at this guy here, this is the same thing duplicated 4 times. There's 2 resistors that go with it. If we wanted to be a little bit more clever, we could set this up as one room and then duplicate it and then make it so that we just have to do one and then copy the room format and paste it into the other 4 or the other 3, and it'll keep them all the same every time. But for smaller things, I just delete the room and it's not really a big deal. So the first thing that you'll want to do is kind of just start placing your parts where you think you want them to be relative to everything else. So the Robo Rio is obviously an immutable part of it. We want to make sure that that matches. And what you'll want to do with this part of it is go look and see, is the D ground on the right-hand side or is the D ground on the left-hand side? If we pull up our Robo Rio page here and search for the I2C, we can see that, okay, D ground is on the left, SDA is on the right. You can also physically look at your Robo Rio. It's got the markings on it to show that D ground is on the left, SDA is on the right. So that's the orientation that we want it here. And then you want to think about the flow logically of your board and where things go from there. So the next thing is going to be your U1. That's your I2C switch that gets connected to it. And you can kind of look a little bit close to see that the clock and SDA, you can kind of follow those rubber bands to see which side it is that's going to the Robo Rio connector. When I rotated it there, you can see this side all has things going over to the connectors, the JST connectors, versus on the top right here, this is what's going to the 4-pin Rio connector. So spacebar is what rotates parts. That's something that I forget to tell people. Also, I might as well show this part now. So right now, all of the parts load up on the top side of the board. But if you think the design through, what you'd probably want to do is have all of your parts on the top side, except for the 4-pin header, because that's going to get connected to the Robo Rio. So if we go back into 2D mode here, you can hit L, which flips it to the bottom side of the board. There's other slower ways to do it. I'm sure I can probably never remember the slower ways to do it. I just get so used to the shortcut keys. But L flips it over. Speaking of the shortcut keys, there's under help, there's the shortcut keys that will bring up a web page that tells you what the shortcut keys are. And that can be useful as well. So anyways, now I hit L. You can tell it's on the bottom side because this is slightly darker. And let me actually go through what some of that stuff means. So in a PCB dock or in the PCB library footprint stuff, you get these other things down here. So these are the different layers. For some people, this may kind of make intuitive sense. Your PCB is pretty much several sandwich stacked together of copper. And so your top layer is a layer of copper, your bottom layer is a layer of copper. And then there's some other things in here too. So top overlay it's typically like the white text that you would see on top of the board. It doesn't electrically do anything. It's just informative for the user. And so you can see that there's a different color in your tabs down here. The top overlay is this bright yellow. This bottom overlay is this kind of ugly yellow, dirty green gold. I don't know what that is. And then there's some mechanical layers and the other one that you might want to keep an eye on, which I don't actually see, top solder. A real quick explanation with top solder is that this is the what gets masked out. And so all this copper would be exposed, and then they put over this green lacquer material that kind of coats the copper to protect it. But this purple area masks that out. And so that means that this would be exposed. So it's usually useful to make sure that you've got a little bit of gap between your top solder masks or bottom solder mask, because that means that that covering material will go between here, which means that when you go to solder it, sometimes you can be really sloppy and just put a big glob of solder and then go touch the pin with your soldering iron, and the heat will pull the solder into it and remove any kind of solder bridges between pins, because at that point there's nothing for it to connect to down here. So if you don't have too much solder, you can use the heat to flow it over, and then if you've got a gap between your mask, that helps prevent the bridges there. So the wizard that I used actually made the solder mask so big that I had to go and modify the pins to reduce the solder mask a little bit and have a gap between there. Let's see, was there another thing to explain with the layer stuff or the PCB? Yeah. So you'll also notice this is kind of just an introduction of some of the things that you can do in a PCB dock. Remembering that I said that those PCB panels down here can be important. If you go and do PCB filter and add that in here, you can add in a filter and then decide like what it is that you want to do with it. So for instance, I think that the designator text here is all too big. And so I can do a filter of is designator. I can choose to have it select anything and then do apply to all. And now it's gone and grabbed all of just the designator text here. I can go into the properties and modify that text for all of it. So now maybe instead of 60 mils for the text height, I want it to be 40 mils, and it'll go and modify it. And maybe instead of doing a stroke for the font type, I'll do true type and Times New Roman, that's fine, whatever. And now it's much smaller. And maybe that makes me happier. Maybe it makes it a little bit easier to read the board because it'll be a small board anyways. Oh, the other thing that I didn't explain that I already have done is if you hit Shift S, Shift S, it changes between showing all layer types or just the one. There's 3 different options. So let me show, also when you do this apply to all, now it's a mask. And so you'd have to hit Shift C to clear it. So right there, it was masking out anything that wasn't the designator because that's what I wanted to modify. Shift S will change it so that now I'm just looking at things that are on the top layer. And if I hit Shift S again, it really hides everything that's not on the top layer. And then Shift S again now brings up everything so I can see everything, all the different layers. And I'll show some more examples of that later. Additionally, whether you're routing or if you're just looking at a single layer, hitting plus or minus cycles between the different layers. So I'm hitting plus, that's interesting how it's showing that in the Karnak there. Hitting plus and minus changes the layers. You can hit star and it'll go just between the top and the bottom layer. And that can be useful when you're routing things. I'm gonna go back to our normal view here where I've got everything. And at any rate, what you would want to start doing is now place all of your components around where it is that you want them to end up being. So maybe you'll have something that looks about like this. And what you'd want to do is check and make sure, okay, SC3 and SD3, and that's going to this board. So that's the part that I want to have there. You don't want to do something where you're like mixing these things up. Hopefully that makes sense. Again, spacebar rotates, spacebar rotates. And now you can see that looking at these rubber bands, they're crisscrossed, which means that the tracks would have to do something too. And it just makes your life more difficult. So this early part is really useful to try to be smart about how you're placing the different components. Another thing that can be useful is when you've got a component or you're doing an action, hitting tab will bring up properties. Let's say real quick that I wanted to just place a track between different things. So I'm going to start laying down copper between how two things are connected. Oh, sorry, this isn't the right way anymore. There we go. So the SDA line, you want to click there. And if you pay close attention, you'll see that the cursor kind of changes to have a big circle around it. And that lets you know that you are actually selecting that net. So you could do that, and then it blocks everything else out and just shows you the highlighted part. You can also look at where your rubber band is, because that's trying to tell you where it is that it's trying to go to. So you would go there until it connects, and then hit escape to back out of it, and you could go start trying to route the next net. And so you might go something like this over here. You wouldn't want to actually start routing these nets until you get everything placed roughly where you wanted it to go. I was doing that to show actually the thing that I didn't finish yet, which is if you are in the middle of doing something here and you hit tab, it brings up the properties page and kind of pauses it over here. So you could change the width or whatever it is that you're doing. And then you can come back over here. And then the other thing that might be relevant is occasionally while you're doing things, hitting spacebar will change how it works. Sorry, you can see that, oh, maybe you can't. I thought it was going to show some text, but if you watch here, you can change that. It changes how it's routing by hitting the spacebar here. So there's a bunch of different keys to do things. I'm actually going to go and kind of jump ahead a little bit here. What I've done is I've got SVN on this, and so I can go and this is, oops, let me update to revision. And which one do I want? I want to have the rough physical layout. Oh, probably doesn't like the fact that this is open. Don't want to change or save any of those changes. All right. So this is now where I've placed the components roughly where I think they would make sense to go. So we've got a pull-up resistor for the reset line of this I2C switch near the RoboRio and the voltage. We've got the resistors and the JST connectors near each other, and in positions that it reduces how much overlay or crossovers there are in the rubber bands. But the next thing that's kind of important is to actually define what your board would look like. If you've got your components roughly where you think you want them to be, I've got 4 mounting holes. That one's not quite in a good place. Something that I've neglected to mention is G is the grid shortcut key. And I like this one a lot. So typically if I'm doing any kind of general placement or placing lines for the what I'm about to do, I like to make sure that I'm going with a big 100 mil. Or if you're in millimeters, if you want to use millimeters, if you hit Q, you'll see down here at the bottom it changes between millimeters or mils when I hit Q. That's what your default units are. There's also the grid showing how big the grid is here. So we want to define our board outline. And so if we think about how the RoboRio is, there's other things above and below this. So we need to have kind of a notch here for this connector. And then the rest of this, in this situation, is just going to hang off the side of the RoboRio. These mounting holes will have to be supported by some standoffs or something like that. And so you want to put this on, I like to put it on mechanical layer 1 on something that other things aren't at. So I'm going to place line PL, and you would just pretty much just draw what your shape is that you want. You can go and fix some things afterwards. I'm trying to speed this up a little bit so I can try to take some questions if I can. And so this is not a great board shape, but this will work for what I want to show next, which is now we want to actually make the board that shape. So I'm going to make it so that only mechanical layer 1 is showing, and by hitting the Shift S, and then I select those components and I go Design, Board Shape, Define from Selected Objects, and now the board looks like this. And so if we look at the 3D model, oh, whoops, I've got this on the wrong direction here still, but this gives you an idea of what the board would start to shape up looking like. And so I'm actually going to kind of jump ahead again to the final project that I did earlier today to show some of the different things. Yeah. So I've got about 10 minutes left. There's a lot of things that I'm kind of skipping. There's under the Design Layer Stack Manager, this is where you would go add additional layers. For most FRC stuff, you can get by with just 2 layers. You should be able to get by with just 2 layers for anything that you would typically see a team do. I added some layers partially just to show them here. For Osh Park, the company that I would typically buy these things from, you'd want to set these as signal layers. You would right click in here and you would do insert layer above or below. And that would add additional layers if you wanted to go that route. I also did some things with polygon pores to show those. So when you hit P for place, you can do a polygon pore here. And you would basically just draw a shape, and then whatever, this ends up being like one big trace. And so you would double click on it, set it to the net that you want it to be. So it could be, 3.3 volts or ground or whatever the case may be. I'm going to delete that because we don't actually need that. And so this is what the final board is that I looked like or kind of made up earlier here. There's some different commands. VB flips the board, VF makes it fit, 9 would rotate it 90 degrees, things like that. There's a lot of different things you can do there. And let's say that we've got this board finished now. We've done a design review of it. We're happy with it. I wanted to show these layers here. You do the polygon pore. I just have these connected to D ground and 3.3 volts. I think, yeah, we only have a couple of very small things on the bottom layer because I don't know, I tried to keep everything on the top layer as best as I could. So now we've got the board done. The next thing that you want to do is in your out job file here, you'd want to go and create the files that you need to be able to actually go off and manufacture it. So under the folder structure is where all these things are going to point to. You would come into your project here. These wouldn't exist yet. You'd have to go add new fabrication output and select Gerber file and do the same thing for the NC drill files. And so when you do those things, you'd double click on your Gerber setup, go into your layers and select all the different layers that you want to actually go and manufacture. So the top overlay, the top solder, top layer, layer 1, 2 are the 2 intermediate, or the 2 that are sandwiched in between their bottom layer, all that other stuff. You actually probably don't need the top paste and bottom paste, but I'm just leaving it there. And so when you do that and have those things pointed to the folder structure, I'm actually going to remove this step from it real quick. You may also want to go and change how this is working. So if you do release managed and you do the defaults here, it would end up separating out the NC drill files and the Gerber files, which maybe is a little annoying because you need to zip them all up for Osh Park. And so I just want one folder that has all the Gerber files and the drill files. The Gerber files basically define what each layer looks like for the manufacturer to go and make each layer and then sandwich them together. So we do that, we generate content. And if I'm gonna show the folder in just a moment that this was done in. So this is the folder that the project is in. There's the project outputs folder, and all of those were in this manufacturing file. So you can see that I just made this 642. You'd right click, send to zip, wherever that's at. right click, send to zip, and you get your manufacturing files here. And then you go Osh Park and just drag and drop that zip file here. It's going to process it. And then this is a really important step. You want to look at each one of these layers and make sure that the what they show matches what it is that you'd expect it to be. You'll get some notes or warnings. If you get any errors here, you really need to go back and figure out what's going on. This is letting you know that you have to buy a minimum of 3 boards. It'll cost a total of $57.70. There's lots of ways to make that cheaper, making it smaller. You'd hit continue to actually go and inspect each one of these. So the board top, this shows what it will look like on the top. It shows what it would look like on the bottom. That should hopefully make sense. You can go and inspect it, make sure that that's all good and right. The drills, you want to make sure that all the holes that you expect to be in the board are there. In particular, like I wanted to make sure that the mounting holes are there. And then it shows you all the other types of things too. So this is the copper on the top layer. So you'd want to make sure that all of that looks right. And then this is when I noticed that how I had something set up before was wrong. In Altium, it does power planes as a negative, but Osh Park wants them to be a positive. So I had to change it to a signal layer and then do the polygon pour instead of doing a plane so that you get the positive. So by looking at that and seeing that it was just an outline rather than all of this being filled in, that's what told me that it was done incorrectly. You want to make sure that your board outline is right. And basically just look at every one of those. You could go through in order and that would be it. You'd get your parts. Something else that can be useful is if you use that manufacturer part search that I talked about earlier to assign your link parameters or the part parameters to your parts. And then this will open up here. If you create this bomb dock, it will automatically populate all the different components in your board as well. So you can see the mounting holes, that's not an actual part. You could put a part for like your standoff or some bolts there or something like that, and you would be able to get an idea of how much the whole board would cost. You can see, obviously, like I said, buying the Adafruit part would be the right thing. Just by buying 3 of those, that'd only be $21 as opposed to the $57 for the custom PCB. But all the individual components on the board are relatively cheap. It's all the PCB cost that's expensive. You can include that also in your output job file here. When you do a PDF, I like to add new documentation for the schematic prints. You can also add in the bill of materials. You can add in a 3D PDF. That can be nice too. And then you might want to create a new folder structure. So you would add new output container folder structure and create a new one for a step file of it so that your CAD team can add it into your Onshape or your whatever your CAD program is as well. So this will be, I think, the last thing that I show here. So this is the board. Of course, I need to refresh it, but this is the board that I then imported and did a mate to make sure that, okay, physically this fit in the Robo Rio where I would like it. There's obviously more that you could do to make sure that all of it's right. You can make it cheaper by making it smaller. You could have the board be over the Robo Rio instead of hanging off the side of it if you don't have an MXP or anything like that. So I think I'm kind of running down on time. I don't know if there are any questions, so I can go ahead and call it quits there and take questions if there are any.
Thank you so much, Andrew. Yeah, we actually do have a lot of questions. That was a lot of information, but it was super interesting. I'm excited to see what we can do with that. I think the first question we have from Nico is, how much does it cost for an individual license outside of school?
It is expensive. So I don't know the actual number. I have it for work. If you're not getting it through school, I think it's on the order of like thousands of dollars.
Got it. Okay.
So, and yeah, I mean, workplaces will get it for, they typically expect to sell it to companies for like 20, 30 seats or something like that.
Okay. So it's like similar to, other CAD programs or Photoshop or.
Yeah.
Like.
Yeah. If you're not using it for school or don't have other access to Altium, definitely look at KiCad or Eagle instead.
Quick note,
Okay.
Can you stop screen sharing because it's the biggest thing they see on Zoom?
Sorry.
You're good. No worries.
Forgot about that. Some of this stuff we still have to work out. So another question we got from, I think, Rickant Martin on Twitch is, they asked how smoothly does this run, but I think like a better translation of that is like, what are like SolidWorks, you need a beefy computer to run, but Onshape is better about that kind of stuff.
Yeah, I think Altium is sometimes resource intensive, depending on all that is that you're trying to do with it. Sometimes generating like the step file might take a little while. I haven't tried running Altium on a lower end computer, so I don't have any firsthand experience to go on that.
Okay, that makes sense. Another question from that one rival on Twitch. They asked what program you were using to display your keystrokes on the screen. That was actually super cool to see.
Yeah. So shoot, now I can't think. Nick, Cat and Cookies on Chief Delphi. I watched a couple of his Onshape videos and he had that, and so he linked me to it. It's called Carnac, I think, CARNAC or something like that.
Like the old predictions account in Chief.
I guess, yeah. I have no idea, but yeah, it's super cool. I think it's useful for videos like these, especially when you're hitting shortcut keys all the time. So I appreciated him doing that in Onshape, and I wanted to do that here as well. Okay,
sweet. So Carnac, and we'll try to see if anyone can find a link to that. Awesome.
Yeah.
Another question we got was, does the software provide recommendations on resistors and capacitors, like when they should be used between components?
No.
And okay.
So what the Altium will help you do is like you can do a search and find out through the manufacturer part search or the integrated devices sometimes what some different values are readily available. But all the design stuff is stuff that you got to do outside of Altium. Like all the I don't know, the real electrical engineering work is stuff looking in data sheets is a big thing. A lot of times data sheets, especially if it really matters, will have suggested, actually, so I'm going to share screen in just a moment again, if I can. The TCA part, for instance, had a typical application that showed that. Let me see if I can find that. If it takes too long, then, okay, here we go. Let me share screen. So I think that's a great question. Data sheets are your friend, super important to look at all of that. So there's this typical application here, and this shows a little bit about how it's expected to typically be connected. Shows the pull-up resistors on your data and clock lines. And then if you look just a little bit further even, it's got a example layout, and that shows having a bypass and decoupling capacitors. So this data sheet in particular doesn't say suggested values for the bypass and decoupling. You'd have to do a little bit of research for that. Some other data sheets will tell you very specifically what it is that they recommend that it should be. It's enough the importance of being able to read a data sheet. If you can read data sheets, it'll help you immensely in college as an electrical or computer engineer.
Got it. That makes sense. So I think this is from the same person. This is a seg9585 on Twitch. They also asked, how does one learn where and why to use inline components?
So as far as inline components, I'm not entirely sure what is meant by that. If it's meant like a through hole versus surface mount or something like that, it's a lot of just the specific application. You learn a lot from trial and error doing some research on the internet. I don't know that I've got a real great answer for that. And sorry if I misinterpreted the question, but.
That's totally fine. This is a giant area, and
yeah.
You work in this professionally, and thank you so much for this. I definitely learned a lot, and I hope I get to play around with this.
And I'm happy to answer any further questions either through Chief Delphi or Discord. I'm a Hartnett, I think, in both, and so you can either send me a DM or put it in the Altium workshop thread or whatever. I'm happy to take any questions I can there.
Awesome. I think your presentation is linked there, but after Beach Blitz is done, we'll try to release all the videos as well as all the presentations from all the presenters. So hopefully everyone should have access to this afterwards.
Yeah.
Thank you so much, Andrew. This was a lot of fun.
This was super fun for me. I feel like I'm the opener for the opener for the opener. You guys have such a great lineup this weekend, so I'm thrilled to be a part of it.
All right. Thank you, Andrew.
Thanks.
Thank you.